Okay, yeah, so there was one, when I first went to Taiwan, actually I got to a place called Hsinchu, which is somewhere over there, which is basically the science park of Taiwan. We have a National Center for Theoretical Science. It's actually quite similar to Nordea, except that it's one country and not 5 countries. Okay. Well, anyway, so I left and I moved up to Taipei at this place. So I would be talking about something actually pretty simple. I only started thinking about this topic only a few months ago, and so just would like to say something about some of the things that I got. So the title is up there, Bose-Einstein condensation and the artificial spin momentum interaction. This word, of course, actually more correct maybe this one, because it's sort of man-made. It's not. Anyway, so if I would like to be fancy, you can use the word non-abelian gauge field, but the effect that it is non-abelian doesn't have much to do with what I would be actually be talking about. The things that I have been would be saying basically already posted right before I got on the plane to come here. So this is basically the plan. Just to warm up, just remind you something about gauge field in quantum mechanics. You heard something yesterday already. Just for the benefit of the people who are not following the literature in this particular area, I would just like to summarize. In fact, there are experimental efforts out there trying to make these gauge fields. So experiments by Spielmann. Then I will proceed to something that is closer to this talk to make it the gauge field is sort of is non-abelian. I'll give some motivation. I came from condensed matter, so it just looks interesting to me that you would have a similar kind of coupling term also in cold atoms. So that is at least that is what got me interested in this problem. Then I will talk about a particular scheme that would may be able to generate this particular field that I will be talking about. And then this is actually the main thing that I would be covering in this talk is what exactly would be this spin momentum interaction, the effect of this spin momentum interaction on Bose-Einstein condensation. I mean, what are the things that you would see? As I said, the fact that the non-abelian nature it would not be apparent in my talk. But if you play around with it, it may be. So, but at least not within this hour. So gauge field in quantum mechanics, the most familiar example is this textbook example that you have a charged particle in magnetic field. As I said, we heard about it yesterday again. So you have a Hamiltonian that is quite, I remove all the C's and E's because eventually there will be an artificial gauge field. So the kinetic energy term is has a gradient on the face, but you minus this vector potential. And for a magnetic field, then we have, of course, the curl A is B. The vector potential is physical in the sense that, I mean, at least that is, we do not know any other better way of doing it. And in fact, we see this from this thing, Aharonov bomb effect, that the particle can sense the vector potential even at places where the magnetic field is zero. So this is really real. The fact that we introduced gauge field in the last transparency was, of course, the fact that quantum mechanics is described by a wave function at which you actually have a phase.
But how can you feel 10 different values at once?
Say it again.
You say A is real, but how can you feel 10 different values at once as one?
10 different values.
No, you have different A at a given point in space.
Yeah, so I totally agree. So it's still pretty weird that after we introduce the A, still just the integral of A dot dl is sensed.
So you still feel the curl.
Perfectly agree. Well, no, a harmonic form defect can have a flux tube and the particles go around. The curl
But it has to go around
everywhere.
It has to go around. If it doesn't go around, you know nothing.
Go around.
Yeah, if you cut the ring, you'll never know it's there.
But it doesn't have to pass through the point at which curl A is finite.
That's right.
Okay, so good point. So anyway, so of course that's the situation here, as I said, because is because we have this quantum mechanical wave function, and we measured only psi square out, and so you can play around with this gauge transformation here. And if you have a different gauge choice of the gauge, then of course you end up with the ordinary gradient would generate this extra piece, which I write A of chi because we can act the gradient on this phase. Now that is just a remark that already made. So this vector potential is in fact, I mean, there's a degree of freedom that you can actually choose. So this is textbook UML. But what is more relevant to this talk is that if you regard this as a kind of a basis, then you write the wave function. So this is your basis, then you write your wave function as some coefficient times this basis. The same algebra would go through, and then now you would actually have a vector potential that you actually produce. Now, that is sort of convenient to understand what I would be talking about next. So let me just say a little bit, a few words about some of the experimental effort out there. You have he has a cloud of atoms which with 3 levels. These are the sublevels of rubidium. Fu1, so MF with 3 values, and so he have just 2 Raman beams that couple the atoms. The details doesn't matter. What it matters here is that there's a wave vector difference between these 2 Raman beams. So the coupling between these 2 terms after you eliminate all the things that you don't want has a spatial dependence. So 2 IK Now you can write the coupling in that basis, but you can trade away. You remove that phase difference, this phase dependence in the coupling, but at the expense that you actually change the okay, so originally, before you have the coupling, then you have 3 states, 1, 2, 3. But you can remove the position dependence of the coupling here, and use paying the price that you actually put in the extra factor here, which is just what I said in the last page. So then the physics is actually easy to see now, because if you ignore the coupling again, then you have just 3 parabolas sort of displaced. If you put in the coupling, then you generate avoided crossings, and then the minimum of the energy is sort of shifted. The experimentalists can check it by turning off the cloud and actually look at the momentum of the atoms in each of the MF sublevels. So of course this part is basically I was just talking about a uniform situation. Then it's just, you can say that it is a matter of labels only. But the fact is that these detunings would be magnetic field dependent, and so therefore by choosing a magnetic field that is position dependent, this minimum can actually move from place to place. So then we would have a kinetic Hamiltonian, which you minus, this is now the shift in this position, which in turn can be controlled by the position-dependent magnetic field. And so therefore you can actually produce a magnetic field with actually a finite curl, so that is actually non-trivial. And as you also heard already yesterday, in fact, the atoms would just respond to whatever Hamiltonian that is given to them, and then you can actually create vortices in Bose-Einstein condensate. Okay, so that was it for the abelian case. If you have a multi-component Bose-Einstein condensate, then instead of a scalar order parameter that has been in the previous few graphs, you would actually have, in general, if you have n component and you have an n component column matrix for this particular wave function. Correspondingly, generalizing what I had in the previous few graphs, then this one would become n by n matrices. In general, these matrices do not necessarily commute, and so therefore they are non-abelian. Of course, you probably know that the interest in abelian gauge field is the hydrogen physicists particularly love it because that is actually describe the elementary interaction between particles. A very popular scheme of producing well, actually there are several of them to generate non-abelian gauge field. One is the tripod scheme, which I would talk about in this particular talk, but there are other schemes out there. It's not clear to me at the moment which one would actually be realistic. Maybe none of them are. But anyway, so the other scheme is that one uses Raman pulses with controlled energy, controlled detuning and so forth. That allows you to hop from one side to the other with a particular phase, and when you hop to the other, which is also depends on which sublevel that you started with. So that you have a sort of a spin-dependent gauge field. That is in particular by Peter Sola and so forth. A lot of people have written on that already. As I said, I would be mostly talking about this one. Actually, there's a new experiment which claims to have a non-abelian gauge field, and I have not seen anything published on it. I only see it that is quoted in the preprint by Jason Ho. I would not be talking about this one in particular if there are people who are interested in that. I'm glad to discuss. Okay. Now this is the so-called tripod scheme. So this is how it works. So actually proposed back in 2005 already. So you have three sublevels, just like you can be the rubidium Fe1 sublevels again. The 1, 2, 3 are not necessarily going from -1 to 1. I mean, you can switch the order if you want to. And they couple to some other atomic levels up there. Maybe that is correspond to let me just say it. So this you can couple it to the orbital angle between 1 and so this one has the right quantum numbers, and you can at least theoretically it can be chosen like so. If you have this particular coupling, then one way of looking at it is that you make a unity transformation within this particular 1, 2, 3 basis. You can actually see very easily that in fact you can make a choice so that there are two states that has no coupling whatsoever. That is known as a dark state in the atomic physics literature. And then there's a bright state which does all the coupling to this level called zero. I draw also a detuning here, so in principle you do not want to be accepting on resonance. So if you have that, then these are the only one to couple. They would split away from these two dark levels, and then you have an energy level diagram look like this. So then we would eventually project all the physics onto these two dark states, okay? Assuming that the splitting of these two states are far away from this, these two dark states. Mathematically, you can actually, it's actually more explicitly, it's like this. You have a Hamiltonian which couples these states 1, 2, 3 to the state 0, like this, and you can choose say the dark state so that the coupling between these two terms actually cancels, and you can choose the third one so that again it cancels. So those would be the dark state. To start with, I can stick with the entire 4x4 Hamiltonian, including all the states. You can do 1, 2, 3, 0, or you can use P1, P2, P1, 0. Then, by the same thing that I have said, because I actually, because of the position dependent of these couplings, or I have not said what exactly would be. So, in general, this thing can be made position dependent. You will see a little bit later. Then all these states are position dependent, and by using the in the position dependent space, then you generate a vector potential, as you have seen before. So then the kinetic term is modified to be something like this. So at this moment, it's all still 4x4. I'll write down a potential V that in general takes into account the fact that the states in general are not exactly of the same energy, or they feel the same, different trap potential. So if the other states that are split are sufficiently far away from the dark states, then I can consider all the physics in the submanifold that I keep, which are the dark states. So I can reduce now the Hamiltonian to 2 by 2. If the off-diagonal elements are small compared with that splitting, then I would still have the truncated vector potential. But then there's one thing. This potential V is again the one that I have explained before. It's the energy, single particle energies. And there's another term that would be generated because the original 4x4 A square would have a term that is in the lower manifold by, if you actually take into account the A square, okay, by having the middle element that is in the off diagonal. One thing that should be said, this scheme is not clear whether it works because you need to prepare your atoms actually in the dark state. We'll see whether it can be achieved in the future. Now, so that was general. So I want to talk a little bit about the particular two forms of the interaction that would be of at least interest to me as with the condensed matter physics background. One is so-called this Rashba term, and one is the this is the Dirac Hamiltonian, the sigma dot p. So this is a px sigma y minus py sigma x. This one you also see in I think yesterday or the day before. This is a term that arrives in graphene, where sigma is in the pseudo spin space of describing the sublattice. For the Rashba interaction, it actually arises in many contexts. Spintronics, surface states of topological insulators, and non-central superconductors. I'll just show two view graphs of these. These are materials where the bulk is actually insulating, but topology requires that surface states exist. And there's actually a single Dirac cone, and the spin direction that is dictated by symmetry. This actually has exactly the form that I have written down earlier. So C cross P dot sigma is exactly Px sigma y minus Py sigma x. This Hamiltonian describes the surface states of this particular material. This one probably not that many people are familiar with, but I went through the program of this workshop, and I think Arthur was here before, and he probably has talked about this one. If you have a system with a up-down asymmetry, in general, the normal state, the Hamiltonian allows you to have this term. I myself actually come from superconductivity, so this is a particular example that this term sort of naturally arises, and it has a very dramatic effect because it breaks inversion symmetry, and therefore it makes us singlet and triplet superconductor. Originally, I was trying to talk about this thing, but anyway, so I decided to change my topic. And, as I said, for those who have been here long enough, you probably have heard the story from Adlerberg. Okay, so now back to this tripod scheme. You need to introduce a position dependent of the omegas, and actually there are, you can have many different ways, and then of course generate slightly different results. I mean, but let me just stick with this particular one for the rest of the talk. So some of the things I will be talking about would be very specific to this particular scheme, some of the details formula, but some of the concepts would be independent of this. Okay, I think it should be pretty obvious, and I don't have to make that particular remark. So, so you have in this case 2 Raman beams. Actually, you need 3. 2 of them counter-propagating with the same intensity. One has position dependent e to the minus ik0x. The other is e to the ik0x with the same intensity, which I conjugate by omega times sine theta. The third beam comes like this with the position dependent of e to the pik0c intensity written as omega cosine theta. This is chosen so that if you square all of them, you add them together. Oh, sorry, it's absolute value square. Then you get omega square. So, you can actually change this thing a little bit. I mean, you don't really have to be exactly this 90 degrees. I mean, actually the results you can get something, some very similar results. The crucial point here is that they just introduce the position dependence from X and then C, because we want to generate 2 components in the gauge field. You can work out the dark states just as what I have shown you before. These, you have to choose that it is orthogonal to the Hamiltonian, but I can add some extra phase factors, which is just for my convenience below. So there's absolutely no consequence of these extra phases. These cosine theta prime, it would disappear very soon. Okay. So I choose a particular value for it just to get rid of a scalar component of the vector potential. And then the vector potential can be shown to be like this. So in this case, then we call that the kinetic energy is like this. If the Fourier transform is p minus a squared, then the coupling is you have a p dot a term, which if you write it out, it looks like this. And then it has exactly the Dirac form, except that in general it is anisotropic. Depends on this is, remember that was the ratio of the intensity between beam 3 and the total. Okay. You can see, recall the fact that the vector potential is produced by the gradient, and of course these x hat and c hat are produced by the beam direction, and you can actually choose the different ones. So they are actually sort of arbitrary labels. Sigma x and sigma c also depends on which choice of the 2 dark states that I call D1 and D2. So in some sense, you can also rotate the Hamiltonian artificially. So that's why the anisotropic Dirac and the anisotropic Rashba in this synthetic spin-orbit interaction is actually in fact identical. It's just a matter of label. something else that you generated by the laser beams are these potentials. The phi that I explained before, it comes from A squared. And in general, you have, as I said, the original states 1, 2, 3 do not necessarily have exactly the same energy to start with. You can have Zeeman fields, and you can also have projective Zeeman fields. And so these are in general not either. But the general form, you can see is, in fact, so in general, apart from this kinetic term, you would have terms in the pseudo-spin space that are actually like effective Zeeman fields. You can have sophisticated ways to cancel them, but I will just keep them because I think in general they are there, and then they actually affect what you actually observe. Now, I would be talking about how this Hamiltonian affects the Bose-Einstein condensation. So I will start from one piece of the Hamiltonian and then add the other and so forth. So that is the full thing, single particle term, the kinetic energy, plus the phi that is produced by laser field. V is the original atomic potentials, plus of course interactions that have not been done yet. So eventually it would come. So let me start with one piece. So that is the ordinary kinetic energy, P minus A squared. You square them all out. Then A squared is just some constant, which you can throw it away. Now, then you have this term, which of course I have already shown how it looks like before. So in general, the dispersion is no longer P squared, because if you go off a particular direction in momentum space, if you choose the right spin, you can either go up or go down, so it actually has this splitting over there. It is not split at momentum equals 0. So in general, it has a dispersion that looks like this. In general, it's also anisotropic between X and C. Okay, so that will come a little bit later. So then there is a very peculiar situation at which you can choose the coefficient of these two to be the same. So if you, as I said, this coefficient is just omega 3 over the total. If you choose correctly, then it is completely isotropic. There are a lot of people who discuss that, but actually there are not that many people who discuss the consequence of Bose-Einstein condensation. But I will skip that one because that is a very peculiar particular situation. If it doesn't, then there are two cases. If the omega 3 is sort of weaker than this particular critical value, then the minimum of the energies are like this. This is just the guide to the eye. So this is Px and Pc. There are 2 points that are actually minimum. There are 2 saddle points here. So the rest are nothing. Okay, so that's just for you to look at. If it exceeds the other critical value, then the minimums are at here and here, with the momentum as written over there, with the 2 saddle points. So depends on the so there are all these 4 positions of the in momentum space that are actually special. Now I'm talking about Bose-Einstein condensation, so I would have to look at the lowest energy state. So for my Hamiltonian, for the sign of the Hamiltonian that I have chosen, the spin actually like to point opposite to the momentum. So so if you are here, then the pseudo spin is like to point down, here you would like to point up, here you would point up, and so forth. So right now, if for a different laser parameter, these two states are degenerate, if this is these two are degenerate. But in general, of course, it will be broken by the term that I have thrown away. So this is the single particle term. So in general, it has this X and C component. So let's pretend that for the moment that these terms are small. Then the answer is actually pretty obvious. So if you have this particular situation, then these two minimum would have an energy split by the term Hc, because it like to have the pseudo spin opposite. In my notation, it has to be parallel to the field. So if Hc is less than 0, then it would like to point down. So this state would be chosen. If Hc is positive, then this state would be chosen, and so forth. Okay. Now, if you go back to look at how it actually looks like, so suppose one is chosen, then the state actually has a finite momentum along the c direction. I have dropped the y components already. Okay, these are only the x and c. The y momentum is k0 sine square over 2. This pseudo spin is fixed to be down. So I would have a condensation into a state that is a final momentum state. It's a plane wave state, and moreover, the pseudo spin is actually locked with the momentum p. So this part follows from the dispersion, and of course this part follows from the spin momentum coupling. If you have condensation in state 3, for example, then you would have a different wave vectors, and moreover, have a different pseudo spin wave function. And so this, one thing that might confuses people is that these states are finite momentum plane wave states. However, they actually do not carry current. Because when I was minimizing the free energy, I already demanded that derivative of energy with respect to p is 0, so they are actually minima. And the velocity operator is a derivative of the Hamiltonian with respect to p. So this one I actually have already demanded that the velocity is 0. Even more explicitly, you can actually work out what is the velocity operator, which is p minus a, because you know in ordinary quantum mechanics, you write it down the whole thing. And then when you actually operate on the states that are written down earlier, the v is exactly 0, okay, for all of them. So they are not moving. So back to so for example, let me just look at these two particular states again. So one of them has positive c momentum, the other has negative c momentum with the pseudo spin locked in these directions. Those are the pseudo spin, but we actually measure the real atomic state. So you can actually work out easily what exactly are these particular wave functions, just using the expression of how D1 and D2 is expressed in terms of the original atomic states 1, 2, 3. Then these are the answers. The point being that, for example, if you actually look at the densities, then the different states are characterized by, I actually pasted in the wrong formula here. But anyway, you will see that, for example, this state would have psi 3 squared is actually finite, but this state psi 3 squared is actually 0. So each state is characterized by their unique density. In each of the components. And of course, moreover, if you actually do more, then if you actually release the cloud, and you can also redo the Spearman experiment again. And so each of the clouds would have their own particular momentum. So I will not go through that, so that the idea is exactly the same. So that was just single particles. So assuming that the single particle terms determines everything, but in general, things can get more complicated because you have particle-particle interactions. I would assume that mean field theory applies, so just like in most of the time that Bose-Einstein condensate. So you first ask what is exactly the random Hamiltonian. You can do it by brute force, starting from all the states 1, 2, 3, and do unity transformation. You get a big mess. You get all the coefficients and so forth, which is still useful. But in fact, the relevant portion of the Hamiltonian can be seen very easily, which I will try to explain. Just let me take a particular example that cosine theta is less than that particular critical value. Then I have these two minima that are degenerate if they are have no external field, what I call H whatsoever. The P0 being this K0 sine square theta root 2 in the C direction. So it's plus C and minus C. I This my state labels are 1 and 2, same as before. Then I asked what would be the effective Hamiltonian in the mean field level. It actually turns out to be just very simple. All the other terms, if you start from 1, 2, 3 and make transformation, you have lots of terms, but all of them are irrelevant in the mean field level. The reason is actually very simple, because if I start, so Hamiltonian have 2 creation operators and 2 annihilation operators right in the interaction. If I take the term with 2 annihilation operators, and in particular, if I consider a case where I annihilate P01 and P01. So then when I kill 2 particles with each with P0, and then the total momentum is 2P0. The outgoing, the only choice is 2P0 again. Any other things would be off shell. I mean, it would be, if you remember that thing, there's another branch up there. So a particle momentum P, you can generate these things, but they are off shell. So if the energies are sufficiently low, they can be ignored. Or it's actually momentum is not conserved because the outgoing 2P0 is the only choice. If I income with one of them with P0 and then the state 2 with minus P0, the total momentum is 0, and then this is again the only outgoing possibility. And so then you continue this argument again. So this is would be the only choice. Okay. So this is the only relevant part of the effective interaction. Now, next, if I do the mean field theory, then I replace this thing by C numbers, which are the amplitudes. Then I would get something that looks like this: psi 1 4, and then square, and then psi 2 4. Now I put back my single particle term. In general, I have a minus mu times the total particle number, which is this piece and this piece. So the numbers are signs. Oh, sorry, this is a typo. 2 and 2. Okay, these are squares. And if I put in the energy splitting between them again, these are the HCs. So then it would be the Hamiltonian that I need to minimize. But this is something that actually we have seen before, because this is exactly the same Hamiltonian we have for a mixture between 2 species that are completely different. Okay, so say the would be Fe1 and Fe2 without Raman counting. Okay? So that is something that people have looked at back in some sort of early days of BEC, something like 10 years ago. And we know exactly what is the phase diagram. I draw it here just to remind you. So one of the Camp potential is mu plus h. And one of them is mu minus h. I also suspect that I have the wrong sign here. Yeah, I think this one should be plus in my notation. This one should be minus in my next picture. So the Camp potential for the one species is mu plus h, so it's positive on this side. For species 2 is mu minus h is positive on this side. If they are not interacting whatsoever, then 1 exists here, 2 exists here, so I would have 1 here, 2 here in mixture in this quadrant, and then in vacuum here. If I have a finite interaction between them, these 2 lines would change. So for particularly this case, I actually draw it to be slightly repulsive. If it is very repulsive, then this mixture phase would just disappear entirely, and then you just have something that looks like this. The slopes, I don't bother you with the formulas. They can be expressed in terms of the G-tuners. Now, mixture So now I have a state that has both an amplitude. Now let me be more specific. Look at the particular case where the minima that I have to worry about, I call the state 1 and state 2, as I have done before. So this is my state 1 and this is my state 2. So if I have the so-called mixture, is that I have an amplitude in both of them. Okay, so I will have my total wave function in the pseudo-spin space is the amplitude times this thing and amplitude times this. Then the unique signature, you see it immediately because these two actually has a finite phase vector difference. So for example, if you actually look at the density in the original atomic space 1 and 2 components, there would be an interference term that actually depends on the wave vector difference, K0 sine square vector difference. So in general, it's like a charge density wave for this if you are in this mixture state. Now, if you think a little bit about what I said earlier, you might have an objection. It is a very valid objection, in fact. Actually, before I said that, let me just go back one thing. For a while, I said that I have these things as a mixture. You see that there's no term that couple the phase between phi 1 and phi 2. So eventually, I have something that I write down a condensate involving the amplitudes of phi 1 and phi 2. Now, the energy can be seen to be independent of these two relative phases, sort of trivially, because if I change the relative phase between these two, I can always compensate by shifting the position of C, so because then they come with a different sign. So the standing waves that I create has the same energy irrespective of where that phase would be. Okay, so this is completely degenerate. So that's why, in fact, the energy actually reduces to a mixture and not an ordinary spinor condensate, where actually it depends on the phase difference between the different components. The thing that you might find a bit weird is that now you find that I will have a condensate that doesn't have a definite momentum. It's a superposition of state with positive and negative momentum, so it doesn't have a definite momentum. So you might actually object to this thing. So this is an assumption. This is a very statement. It is an assumption. Basically, I assume that you can have a so-called single condensate situation. It is only possible if I assume that somewhere I have processes actually doesn't really exactly conserve momentum. Maybe the trap or some homogeneities or whatsoever. This is actually. I also noticed from the program that Galinsky was here. I never met him. He actually talked about. I haven't checked exactly what he talked about, but I checked his papers. He actually wrote down, in fact, what was corresponding, what it has been called the fragmented condensate case. Okay, so that is not a single condensate. The single condensate in the sense that I have a macroscopic occupation number of one of the states. So that is definition by OCS. Now, the fragmented states means that you have macroscopic occupation of more than one state. The analogy that I'm trying to make here is in fact what we actually have seen before. Think of a spinor condensate. If you have two levels, actually it was first discussed by Rukenstein before. So effectively spin 1/2 system. That was now just the spin out. So two states, up and down. You can write down a state like this, which then you state that I macroscopically occupy beta times up plus alpha plus up plus beta times tau. So that is a single condensate state. It also it does not conserve spin. Okay. So it doesn't have a definite S sub C. It looks weird. If the spin is exactly conserved, then this is actually not allowed. So you have to invoke some process at which the spin is not conserved, so that you have condensate in this state. We actually discussed a similar situation for spin 1 back in 10 years ago. I did it with Jason Ho. For spin 1, again, you have the similar situation. You can, if you insist that S sub C is conserved, then the states you cannot have the ordinary spin 1 condensate that we described, that you have the condensate into some linear combination of up, 0, and down. But however, we actually also pointed out in that paper, in fact it's something, in some sense it's obvious, these fragmented states are typically very delicate, because if you have a large number of particles, the matrix elements that couple these different states is actually Bose-Einstein. So unless you have a very perfect spin conservation, in general, you would go to a single condensate state. So I'm actually making the same assumption here for the condensate. It is feasible, that depends on experimental details, that you can actually end up with a fragmented condensate and not a single particle condensate. But that has to be a very ideal situation. That's about all. Yeah, so let's see, those are, yeah, so I just talk about the states for a small HC, then I just have all these minimum either here and here. Of course, that cannot be the whole story. Yeah, so I talk a little bit about the case when this HC is not necessarily small. Recall that this HC is automatically generated by the laser field, so this is actually has nothing to do with magnetic fields, energies, and so forth. Okay. So this particular magnitude of this coefficient of sigma c, of course, depends on that particular laser arrangement. Okay, but I just try to illustrate in general what would go on. So, so I will just give you the answer. So in this particular case, then the minimum would still be this state, and so these two, so HC less than 0 is this one and this one, same as before. For the other case, would be a little bit different. So if that thing, remember that if I have no phi, then the two minimums I have here. So if I have finite HC, it actually faces a pseudo spin that points opposite to the external field. So if HC is less than 0, I favor the pseudo spin points down. So the minima of these 2 points actually moves. There is a critical value at which this thing minima actually completely disappears and actually goes back to the state that I call labeled state 1. So for that particular given configuration, there's a critical amplitude for the third laser. Remember, this is omega 3 over 1. That you would actually remove these 2 particular minimum. For these, I would not bother you with the formulas again. So but if, for example, they would have then their own standing. If you have a mixture, then they would have their own standing wave, but then with the wave vector difference. That is dependent on where you sit, and in particular, it depends on which theta or which laser amplitude that you apply. Okay, so I guess that's all I would say. So this is what I covered. The Bose-Einstein condensation with this synthetic spin momentum interaction. There are 2 states. In general, you can have even more. These are the most generic ones. You can have condensate into a final momentum state with a spin that is locked to the momentum. You can have superpositions that will correspond to the ordinary mixture. But of course, the consequences are different. I mean, because then the density distributions are different from the ordinary mixing two species. In particular, they are characterized by the periodic modulations of the density. Two other preprints actually cover similar things. As I said, this paper addresses the unpublished Spearman scheme. This paper also is numerical calculations on a Hamiltonian with a spin-orbit interaction, but they do not express back in terms of the original atomic state. So some of the results in my paper, what I described, is common to this paper, but some of them is not. Okay. So I guess I will stop. Okay.
Some questions?
I want a slightly naive question. I mean, it applies to all these things where you've got trapped atoms, and yet you want an eigenstate which is a superposition of different momentum states, you know, which would naturally sort of separate, you know, because momentum states are not necessarily eigenstates in the potential, are they?
Oh, yeah, that's right. So this one, yeah. So then I actually sort of already invoke some kind of local density, kind of picture. So these oscillations has to be fast compared with yeah. So that assumption has been built in. But there's nothing wrong with a finite vector incident on the edge of the sample, though, because as I said, they have zero velocity. Yeah, they don't reflect. They don't have to reflect back.
What's the realistic value of K0?
Realistic value of K0, the K0 depends on the laser beams. It's actually completely dictated by these laser beams. And I don't know what.
Well, at some point you mentioned this relative to the detuning, right? K0 comes from the detuning in frequency.
Oh, K0 doesn't come from the detuning.
No?
No, K0 comes from this phase vector dependence. This is coming from the.
So it's just
the same as the V.
It's
Same as
the
the
wavelengths of the laser, or
Is that one
or it's the difference?
Yeah, they would be the same units as these guys, for example. I can't remember the numbers. Yeah, it's come from the V. The detuning only comes in when I remove these two states that I don't want.
So it's also on the scale of micrometer. Universe K0.
I don't know, do we have any other choice? Must be micrometers.
Yeah.
So we experimenters.
2K.
Okay.
2K.
Can you have vortices in these systems?
A very interesting question. Yeah, because initially this, I have two answers. One is the preprint that I showed. That there are two preprints that I showed. Originally, their version 1, they say that they would have some vortex states and so forth. And I think they withdraw that. Actually, they changed. They think that is actually not correct. You can actually create vortices again if you have the gauge is actually position dependent once more. I mean, that one then with the ordinary. Just.
I was just wondering that, I mean,
Yeah.
somehow, I mean, when you go to the core, I mean, your couplings are somehow momentum dependent, and you go to the core, and then you have large gradients there. That is it that the theory somehow inherently breaks down as you get to the core? I mean, how does it work?
I haven't thought that much about that. Yeah. So there's there's something that is deceptive. I mean, this thing, you really think of this as a large gradient in the Ginzburg-Landau sense. Okay? But you do have to worry about it that they couple to the other states that you throw away. Right? So those are two different things. Yeah. So if you don't worry about the if your omega is really large that they are very, very far away, the Orring-Kingsford Landau field would still work within this subspace. I mean, the fact that I have a finite K0 doesn't really matter. Yeah, because the Hamiltonian was this, right? So that was the fact that I have a finite momentum condensate actually comes in A. And so the fact that I have a large, so that in fact, I'll put it this way, when the fact that the momentum is close to the place at which actually is minimum, so the gradient energy is actually small. Yeah, of course, then if you actually generate a position dependence of this A, then of course you have another story. And that's what I believe. As I said, I haven't been working on this topic long enough, so it might be something that I have missed.
Other questions? Okay, let us thank you. Somehow have to assume that I'm local and always
Just wait, but that one comes in.
But that's of course
that comes from the adiabatic assumption. So that's the same as this part. When I truncate the 4x4 to 2x2, right? So that was that stage.
Yeah, so in some sense, I mean, it's probably independent of the vortices in some sense.
That's what I'm trying to say.
So,
those are independent.
Vortex thing, I mean, you have vortex core size, which is like a coherence thing.
Yep.
Of course, things might go haywire if this core size starts to be comparable somehow.
Yeah.
To the length scale of where respective potential varies. But I mean, if the length scales are well separated, then it presumably won't make a difference.
Yeah. So basically, they are two different questions.
Yeah. Well, this is an interesting problem. I mean, we are thinking.
Well, the thing that I really worry about is whether the scheme is feasible.
Yeah, for me, I mean.